So today's topic, as you can tell, focuses on extinction. This is not a new concept, this is not a new topic, but it's been brought into the spotlight a little bit because of a paper that was written last summer. That paper is titled Accelerated Modern Human-Induced Species Losses Entering the Sixth Mass Extinction, which for our purposes basically means,
Did you Tom?
You didn't actually know about it.
Okay.
Is it on?
It is technically on, whether it's actually like battery power is a different question.
There's polar bears involved, or not? There's not.
That's not a battery. Oh, no, it's working, got it. Cool. So, yay, extinctions, yay. So again, accelerated modern human-induced species losses, which for our purposes will mean evaluating whether humans are causing a mass extinction. Before we get into mass extinctions, it's worth discussing what extinction actually means. An extinction for our purposes, and these are categories determined by the IUCN, or the International Union for the Conservation of Nature. The first of which is a species that is extinct. A species is extinct when no reasonable doubt exists that the last individual has died. This is the West African black rhino. This is a species that was forced into extinction in 2011 through overhunting and poaching. These are species that we know for a fact, empirically, through looking through their typical habitat, doing exhaustive searches, that we just simply can't find them anymore. Species that are extinct in the wild meet those same criteria as the first for the wild. However, we still have certain viable specimens held in captivity. This is Lonesome George. He is a Pinto Island tortoise, was unfortunately. He was the last remaining member of his species until 2012 when he died, hence Lonesome George. Again, these are species that are extinct in the wild, but we have captured a few specimens that, is that a question? Yeah, what's that?
Is Lonesome George a metaphor for somebody in the show?
Perhaps. Perhaps. Our last category is possibly extinct. Now, this is similar to our first category in that we've been looking for these species and we can't find them in the wild anymore. However, we haven't been able to perform the exhaustive surveys that are required for extinction, in part because these are more recent. So this is the Panamanian golden frog. There's a fungus called chytrid, which has been ravaging amphibians in Latin America, which has wiped out species such as this, but we haven't had enough time to go and make sure that they're actually gone. These are also held in captivity as well. So with that in mind, the next terminology is determining what taxonomic groups we're going to be looking at. A taxon being a unit of biological classification, looking at different structures of the hierarchies of animals. The one we're going to be talking about for the most part today is the one we're most familiar with, species. A species being the lowest of this hierarchical chart, which is anything that shares common characteristics and can breed with members of its species, but not with members of not its species. So that's its defining characteristic. Okay, with that in mind, how do species go extinct? There are lots of different ways this can happen, and this certainly won't be an all-encompassing discussion of how species can go extinct. But one major way in which this can happen is through selection. Selection being a process by which certain traits or characteristics are selected for in a given environment due to any number of circumstances. So this could be, the ones we all know about, giraffes with long necks, able to beat out competitors with shorter necks, which then pass on that trait to their offsprings thanks to their ability to survive and pass on that genetic information. Okay? That's basically the process of selection. And for the purposes of our examination of extinctions, we're going to see changes in the criteria that are selected for when something like this turns into a habitat that looks more like this. Whether we're using this as agricultural land, grazing land for our domesticated animals. And most particularly and most recently, thanks to the Industrial Revolution, like this. Again, the criteria that are selecting for certain traits are changing drastically And in this case, faster than species can actually evolve to adapt to those. Evolution is a process that takes hundreds of thousands to millions of years. And as we're going to find out today, the process by which this is happening far more rapidly than they were able to adjust to. So with that in mind, we've got to try to figure out how many species we're losing. We'll come back to this in a sec. But our basic outline here is we're going to try to figure out the extinction rates before humans. Just like any experimental design, this will be our control. Then our experimental variable will be figuring out extinction rates with humans, see if there's a statistically significant difference, and then decide whether this difference might be correlated with human activity. So the first step is really hard, okay? We can try to establish a baseline. However, in order to determine how many species are actually being lost, we don't know how many there are out there, and we're finding 15,000 new species on average every single year. So cataloging and crossing off names that have gone extinct in order to determine the actual rate is prohibitively difficult. Because of that, previous iterations of this study have focused on modeling, specifically the species-area relationship. And all this is trying to take something we know and use it to find out something we don't know. In this case, we have information we know, in this case, habitat. We are aware of a relationship between habitat and the number of species that can exist in a given habitat. Based on that, if we can figure out how much habitat loss is going on, we can figure out how much species loss is going on. And habitat loss is much more easy to determine. Through satellite imagery, long walks in the wood, we can figure that out, whereas figuring out the number of species loss is much more difficult. The problem with this is that it hasn't been very accurate, and it's resulted in a stigma. Typically, when you have information that ends up not being as accurate as you'd like it to be, particularly if it seems exaggerated in order to promote a political agenda, which this may have done, it creates a stigma with the public, and it kind of invalidates any future work that's done on a given topic, which is a really challenging obstacle to overcome. So what our paper has done, differently from the last one, is largely similar. Figure out the extinction rates before human, figure out extinction rates with humans, and finally figure out whether there's a difference and decide whether it's due to humans. But what this is doing that's different is we're not going to model anything out. We're going to miss out on some species because we have simply imperfect information. However, as a conservative baseline, we're going to try to figure out how many extinctions we know have occurred. Only information we know. No more speculation. Let's create a conservative baseline estimate. So, the first step, again, is figuring out the extinction rates before humans. This focused specifically on the fossil records of mammals. Why do you think we would have picked mammals? Anyone want to hazard a guess? No, go ahead.
They have big fossilized bones.
Good, big fossilized bones. That's exactly right. Go middle school. There we go. The same exercise wouldn't be as fruitful with insects, for example. Anything that doesn't have as reliable of a fossil record is going to be more challenging to determine an actual accurate background. So, based on that, we're going to use mammals and extrapolate how many mammals, based on the fossil record, have gone extinct in a pre-human environment. And we were able to determine that there are roughly 1.8, rounded up to 2, extinctions per million species years. Super cumbersome metric. So what this basically means is you've got a number of extinctions per million species per year. And if you think about that, you could also say 1.8 extinctions per 1,000 species per 1,000 years. So you can play with that metric a little bit, but basically what it's saying is how many species we're losing out of a certain number of species over time. Okay? And our goal next is to compare this against the IUCN list of recently extinct species, specifically 2 major categories. One is the most conservative. These are species that we know have gone extinct and can be found nowhere on this planet. This is very conservative. And conservative is looking at species that have gone extinct, species that are extinct in the wild, and possibly extinct species we discussed earlier. Now, the findings of this are striking. we, since 1900, should have seen 9 vertebrate extinctions. Under the most conservative possible metrics, based purely on what we know, we've seen 477. We should have seen 9, we've seen 477. And again, this is looking purely on what we know. No extrapolation, no modeling. So the reality is, unfortunately, that that number is probably much higher than 477. There are a few ways we can break down this information. First, we can look at the rate of species extinction. Compared to the background rate, we're seeing between 8, depending on whether we're talking very conservative, or 22, whether we're talking about conservative, between 8 and 22 times as many vertebrate extinctions as we would have seen in the background rate. Okay? And that's since 1500. There's another way of looking at this, which is if we were to try to think about how many species have gone extinct, and then how long that would take in a normal pre-human environment. In the last 114 years, we've seen 477 species go extinct. Instead of 114 years, that should have taken in a normal pre-human environment between 800 and 10,000 years, depending on which taxonomic group you're talking about. So, obviously these findings are pretty striking. Now, what we want to do next is try to figure out, okay, is there any connection with human activity? Is there anything like this that might have happened in the past that we can compare this to? And the answer, thankfully, is yes. There have been 5 major mass extinction events in the past, the big 5, if you will. And there are some common traits that we're going to try to look for amongst these and see if there's any way we may be replicating this. So again, this is the first one. This will be an important one to keep in mind for a couple reasons we'll go into. Most of these extinctions are resulting in between 70 and 85, in the case of the Permian, 95% of species loss. And many of them involve change in atmospheric composition. The way that happens during the end Ordovician is the sequestration of carbon. What that basically means is for the first time we had plants growing on land. What are plants made out of? Cells.
Carbon.
Carbon. Good. Good. So the formation of terrestrial plants takes carbon in the form of carbon dioxide out of the atmosphere and deposits it in the form of plants. We'll come back to that one later. Okay. The second one, the late Devonian, again, 70% of species lost. Change in atmospheric composition due to asteroids or volcanoes, throwing a bunch of dust up into the atmosphere, preventing solar penetration and thus cooling down the planet. The end Permian, this is the big one. This one resulted in 96% of species loss. And what's really interesting is the thought experiment is this means that 4% of species survived, which is still a pretty large amount. But what's really cool is that those 4% of species, after the recovery from this mass extinction, represent and represent the ancestors of the entire scope of biodiversity on the planet. So every single one of us, including every single thing you've ever seen in your life that's biological, came from these 4% of species. And we'll come back to that later too. Okay? Again, we're seeing change in atmospheric composition here, this time resulting in global warming. A similar occurrence here at the end of the end Triassic. And then finally, the famous one we all know about, the asteroid that killed the dinosaurs, the end Cretaceous. Now, like we talked about, when we have 70% of species lost, it creates a gap. It creates an opportunity for new species, new groups to grow into that gap. And this is what mammals do, resulting in us. Dinosaurs go away. The kind of pinnacle of biological evolution at that time is wiped out, resulting in new species that can grow into fill that niche. So, I want to come back to one of these here, in terms of the sequestration of carbon. Can anyone think of how this might relate to humans? We've got carbon dioxide being pulled from the atmosphere and forming plants on the surface of the land. How does that pertain to what we're talking about today? Go ahead.
Well, this is a guess, but the fossil fuels that we burn are made from the remains of plants millions and millions of years ago, so we're releasing carbon back into the air.
Perfect. Not only that, but we're also deforesting the planet at a rapid rate. Okay? So we're doing this exact same thing in reverse. And this exact same thing resulted in 85% of species lost. Okay? So there are a few ways that humans can actually replicate these processes. The first obvious one is what you just mentioned, climate change. Okay? This is going to be any, and again, this pertains back to the speciation we talked about, where you've got a process by which the environment that an animal, a species, any plants have adapted to is changing so rapidly that it can't adapt to those changes. Okay? So that can be a result of climate change. That can be a result of habitat destruction. There's a growing body of evidence showing that the ocean acts as a mediator for climate change, which basically means that rather than all of the carbon dioxide we're releasing going up into the atmosphere, the ocean actually absorbs a lot of it. But the problem is that has an impact on the ocean too. It actually decreases the pH scale of the ocean, making it more acidic. It turns out when you have an acidic ocean, coral reefs can't grow. So not only are we burning down forests to deposit more carbon dioxide in the atmosphere, resulting in global temperature changes, we're directly eliminating the habitat of terrestrial animals and indirectly eliminating the habitat of aquatic animals, of marine animals. So those are kind of the big three here. There are two other major ways we're doing this. One is through overhunting. Again, growing body of evidence that for the last 10,000 years, we're not even talking about the Industrial Revolution now, since basically the end of the late Pliocene, when basically the last ice age, there were huge animals like giant sloths, woolly mammoths, saber-toothed tigers, massive marsupials, you name it, really big animals that had grown in to fill that niche that was left by the dinosaurs. And for a long time we thought that it was just the end of the ice age that led to their extinction, and that probably was part of the solution. But there's a growing body of evidence that as soon as humans show up on new continents like Australia, all of those massive animals disappear pretty much overnight. Causation? I'll leave that up to you. Certainly correlation. Okay? So overhunting, and certainly today when we've got 7 billion people on the planet who we need to feed, overhunting is becoming a more substantial problem. And the final one is really interesting, is invasive species. When we think of invasive species, most of these previous extinction events occurred under supercontinents. We had all of the continents together under the continental drift theory. Everyone with me here? Continental drift, yeah? Okay. So all of those continents were once linked together. Pangea, I don't remember the names of all the other ones, but there were a lot of them. Okay? During many of these processes, all of those continents were together, which means that any impact would affect all of these species pretty much at the same time. So as we've seen more, the separation of the continents, we've seen more speciation, more specific traits that are being selected for. And as a result of that, we've seen higher biodiversity on the planet than we've ever seen before. Species are more specialized, more niched. So part of what's happening now is through the global transportation network, through global trade, through a lot of these different processes, we're bringing these continents back together, metaphorically speaking. And we're introducing species that have had no interaction with these other species for millions of years back together. And that's resulting in invasive species. And this is going to be really cool because when we talk about most of the species that we're losing them because when we introduce them to a new environment, they can't handle it and they die off. There are some species that when you introduce them to a new environment, it could be because this new environment doesn't feature a natural predator they had before. It features less natural competition than it had before. If it's a parasitic species, the hosts on which it feeds may not have developed immunity to it by evolving alongside it. Through any one of these processes, these animals actually thrive in our human environment. And we'll talk about the consequences of that in a moment. But we can talk all day about whether we have the right to go and extinguish other species and what all that means. But there are a few key impacts for us here, for humanity. The first of which is how much food we can produce. Right now, 15 species of plants produce 90% of our food. The big three produce half of it. If any one of these species were to suffer a blight, a disease, as we know from invasive species, it's going to get spread around the planet pretty much overnight from a geological timescale. And moreover, it's going to wipe out, depending on which one we're talking about, as much as 1/15 of our food supply. Pretty much overnight. That's a huge vulnerability for us as a species, especially one that's growing as rapidly as we are. Moreover, farm productivity gets impacted when we have species like honeybees and other species that naturally fertilize our crops. When they're wiped out, we have to rely on other means by which to do so, such as fertilizer. Fertilizer runoff not only decimates aquatic systems, but limits our ability to access fresh, clean water, which is further impacted when we're cutting down rainforests, which is impacting the water cycle. So basically, if you take food and water, the basic necessities that we need to live, we're drastically reducing our ability to harvest those things safely. And finally, medicines. There are between 50,000 and 70,000 plants that are harvested every single year for medicinal purposes. As we're eliminating the natural habitat for those plants, we're diminishing our ability to A, find new medicines, and B, even harvest the ones we already have. But beyond this, beyond just the impact on humanity, there are some bigger questions. What steps can we take to preserve Earth's biodiversity? For one, we could certainly look to mapping genetic codes. If we have the genetic information, perhaps someday when we have the technology, we can bring some of these species back if we ever, stop the rate of environmental deterioration. Any other ideas for how we could prevent the loss of biodiversity? Jared, just send them directly to President Obama. Okay. The one that's really interesting to me and the one I want to elaborate on is, what does the future of life on Earth look like? Okay. When we looked at the late Permian extinction, 96% of species died off, which means those 4 remaining % of species constitute the entirety of life on Earth today. If you think about that, if we're doing the same thing now, we've got a proverbial Noah's Ark. There's a great flood coming, the extinction that we're causing. And there are certain species that we're carrying with us into it, these invasive species, these species that happen to thrive in a human environment. What are the characteristics that those species share? Is it short gestation periods, ability to rapidly adjust to new environments? Whatever it is, those species are going to be the composition of our planet in the future. Okay. The final, what is our true nature as a species? If it turns out that we've been extinguishing other species on this planet for the last 15,000 years, basically, since we grew intelligent, what does that mean about us? Do we have the capacity to break that cycle and move into a cycle of more environmental stewardship, using our intellectual capacities to kind of rise above our biological needs and actually institute some sustainable growth? This one's really interesting for me too, because as we're looking to expand beyond our own solar system, or even beyond our own planet, we have a very bad track record of dealing with other life. When we think of H.G. Wells and War of the Worlds and all those other sci-fi movies, Independence Day, where there are other aliens coming to take over our planet, that's what we've done to all life on Earth so far. It's hard to think of ourselves as these intrepid space explorers if that's going to be our legacy. Guys, any questions? Go ahead.
So you compared the expected baseline of extinction compared to what actually happened.
Yeah.
So is there a similar statistic for the other periods of extinction?
That's a great question. As we go further back in time, for example, the end ordination, we're having a less reliable fossil record, so it becomes increasingly difficult. I'm not sure if there's been a body of work looking at that, but it would be really interesting to find out, because then we could actually try to figure out whether the rates have changed over time in even normal situations, which would be really helpful as well. Yeah, go ahead.
What are the parameters for a reliable fossil record?
That's a great question. I'm not sure. That's part of the reason they focused on mammals, is because it is more reliable. Reliable, and what do you mean by reliable in terms of knowing exactly how many?
How do they define the reliable?
It's often a case of we don't know what we don't know. We can think that we have a perfect cataloging of mammalian species, but there could be an abundance of other ones that we just simply haven't found yet. So we think we've got a pretty good handle on it. We could be way off. So that's a great question. Yeah, go ahead.
There are theories that other planets in our solar system, I think it's like Mars, used to look like Earth.
Yes.
Was there any indication in the paper saying that maybe that could happen with this extinction versus like just wiping out a majority of species?
That's a really interesting question. I mean, there was no discussion of it in the paper. Certainly, if you look at Earth itself, for much of Earth's history. We're looking at a planet that looks a lot like Mars. So, is it possible? I don't want to speculate with that. But certainly the history of this planet has shown the capacity to have that characteristic. And Mars, like you said, as we suspect, may have had an atmosphere very similar to ours. They may have had running water. It very well could have been that Earth, that the Mars once looked a lot like Earth, and it does. Go ahead.
So, like, this paper says that the rate of extinction has increased since humans came into play.
Yeah.
Does it talk about if, like, the rate of extinction because of humans is increasing? Like, is it higher now than it was, like, when humans first started having an impact?
Yeah. So if we go back to this chart, as you can see, there are certain time scales where the rate is increasing even relative to the elevated rate from before. So if we're talking about, for example, mammals, we were killing mammals off at a greater rate than the background rate, even in the 1500s. However, that rate has increased rapidly coming into the modern era. So as we increase our agricultural land, as we continue to destroy habitat, this is only becoming a more pronounced trend. So certainly that rate is increasing over time. Go ahead.
Do you think that's a result of like human intellectual evolution?
Perhaps. It is correlated with that, right? So if we're looking at the Industrial Revolution, there is a certain change in rate in each of these species, except for maybe other vertebrates, right around the time of the Industrial Revolution.
So isn't that just like survival of the fittest?
Totally. Totally. The difference is we're changing the criteria of what it means to be fit. That's all. So we're not redefining evolution, we're not doing anything like that. We're just changing the criteria that select for certain animals or plants.